Hi, and welcome to this walkthrough of an applied mechanism reaction type question. It's going to focus on something called ozonolysis, which although isn't on any A-level specification, it's just close enough to A-level chemistry to be able to be manageable with a little bit of thought, because it just basically is an application, an extension of some of the mechanism type work you'll have done already. So let's have a look at it. It says that it's a technique used in organic chemistry to break open a carbon-carbon double bond. So if we look at this CC double bond and look at changes, that's one of the carbons, that's the other one. So obviously two carbonyl compounds are made. Now carbonyl compounds are obviously aldehydes or ketones. So the ozone is the reactant that makes this happen. So what they want you to do is draw the structures of the products plural, you'd expect from the complete ozonolysis of the following alkenes. So pent-2-ene first of all, and hexa-2,4-diene secondly. So let's go back to what we need to think about. The key to this type of question is to focus on what actually changes and ignore everything else to avoid getting confused. So although they're just asking for the structure of the products, I'd suggest possibly drawing out the named alkenes first of all, so it's more visual. It allows you to focus and process on what it is that's going to change. So for example, pent-2-ene has a carbon-carbon double bond here, so therefore that carbon-carbon double bond is going to turn into two carbon double bond oxygens. So therefore that splits the molecule into two compounds, both of which contain a carbon double bond oxygen. Now with hexa-2,4-diene, you've got to be a little bit careful here because you've got two carbon-carbon double bonds, and both of them will undergo ozonolysis because, as you can see, I've highlighted complete ozonolysis. So wherever you get a carbon-carbon double bond, this will happen, this kind of template of what goes on. This will take place. So you need to apply the ozonolysis process in your mind to both double bonds in the diene. So obviously what will happen is you'll get this middle part will form this compound because it's got a carbon-carbon double bond either side of it, and these end bits, there's two of them, so they will each form an identical molecule here, ethanol. So this is a more applied part of this question. It says, in another ozonolysis reaction, organic compound G reacted to form only hexane 1,6-diol. Now hexane 1,6-diol is 6 carbons long, and it says compound G has 6 carbon atoms. But a diol is two aldehyde groups, one at carbon number 1 and one at carbon number 6. So what must happen is the carbon-carbon double bond will break open once to make two C double bond O's like we have in the template on the screen. So I've copied over the template from before. We're just using this to think through what's going on. So to make one compound with two of these, the original alkene must have been cyclic. In other words, the ring breaks open. So therefore compound G must be cyclohexene. So why cyclohexene and not another cyclic alkene? Well, because it's got 6 carbon atoms. So I'm just going to show you the equation so you'll see how it works. Right, so this is your hexane 1,6-diol. Okay, this is an aldehyde in skeletal formula form. And you've got 1, 2, 3, 4, 5, 6 carbons. It's been drawn like this so you can see how it was derived from the hexagonal ring structure of cyclohexene. So cyclohexene is your compound G. The carbon-carbon double bond breaks, opening the ring up, and then the ozone reacts to create two carbon double bond oxygens as per the template from the question that's a bit higher up the screen. Okay, so hopefully this has been a useful insight into a slightly more applied question, but one that's with a little bit of thought isn't too hard to tackle. Thanks for listening as always. Until next time, see you soon.